In early 1956, this huge plant on a 3,700-acre site was in full operation, months ahead of schedule and hundreds of millions of dollars under estimates, a significant contribution to our national defense program. Few construction projects in history were of this unusual magnitude or so taxed the ingenuity of engineers and contractors. Here, some of the largest buildings in the world were built to separate the tiny atoms of uranium, utilizing a remarkable process to achieve this in mass quantities. One building is so large, you could put 3 Yankee stadiums inside and still have room for a football field. Almost 10 million square feet of floor space in the permanent buildings. Almost 70 million man-hours in construction. If all the building materials were hauled in a single freight train, 100,000 freight cars would be required, extending more than 814 miles, about the distance between Cincinnati, Ohio, and Wichita, Kansas. And the power to operate this plant reaches an astronomical total of almost 2 million kilowatts, the largest single power requirement in history. This vast construction job was authorized by the Atomic Energy Commission as part of an expansion program to increase production of fissionable materials. Also included in the program were additions to the Oak Ridge and Paducah plants at a cost of $500 million each. Factors most important in selection of the site were availability of economic electric energy, availability of water for both power generating facilities and plant operation, adequate potential labor, and suitable transportation facilities. To understand the position of gaseous diffusion in the atomic energy program, let's look at the sequence of events that produce fissionable materials. First, the procurement of raw materials. From both foreign and domestic sources, the uranium ores are gathered and concentrated. Second, the preparation of feed materials. The concentrates are refined and processed for either of 2 production methods. One, as a uranium metal in rods and slugs for transmutation into plutonium in the reactors at Hanford or Savannah River. 2, as a gas, uranium hexafluoride, UF6, from which fissionable uranium-235 is separated by the gaseous diffusion process not only at Portsmouth, but at Oak Ridge and Paducah as well. The third step concerns utilization of fissionable materials for armaments of war or for purposes of peace in science, agriculture, industry, and medicine. Gaseous diffusion through porous barriers is the most efficient method for separating the lighter U-235 isotope from the U-238 isotope of uranium. The actual separation is accomplished by means of a barrier which contains billions of holes, each smaller than 2/millionths of an inch. The U-235 molecules in the gas, being lighter, move faster and pass through the barrier more quickly. The enriched portion of the gas is then sent successively through other barriers for further concentration. Since uranium contains only 1 part of U-235 to 140 parts of U-238, several thousand such barriers or stages are passed before the required degree of enrichment is achieved. At each stage, the residual gas, depleted in U-235, is also withdrawn and recycled through successively lower stages of barrier. The Oak Ridge operations of the AEC set up an organization designated the Portsmouth area to direct construction and operation of the new plant, to develop design criteria, to select architect engineers and construction contractors, to schedule delivery of critical materials, and of course, to anticipate every possible contingency. Coordinated teamwork was thus achieved between government, industry, and labor, which contributed greatly to the success of the project. Labor and management cooperated to set up uniform agreements, with the result that the number of stoppages for the Portsmouth project is one of the lowest in AEC records. Some of the early planning and organization took place in improvised offices in the city buildings of Portsmouth. Buildings like the National Guard Armory and the Elks Club were crowded with engineers and drafting tables. Temporarily, Even the old farmhouses on the site served as offices for the architect-engineers. 9 architect-engineer firms shared in the design of the plant, and 12,000 design drawings were made, enough to cover about 2.5 acres of drafting tables. In addition, construction drawings totaled 40,000 and shop drawings 16,000. Since construction had to start before all the drawings were completed, contracts with both the architect-engineers and the prime construction contractor were on a cost plus fixed fee basis. Most subcontractors were on a fixed price basis. This advanced planning and scheduling of materials, equipment, and personnel were extremely important because the plant was designed to go into operation or on stream as soon as each unit or segment was completed in a process building, even though construction continued in other parts of the same building. 2 railroad lines, financing their own work, built spurs into the area to haul in building materials and heavy equipment. Groundbreaking occurred on November 18, 1952, and that same day, the cats and scrapers churned the landscape to level out the rolling farmland for the building foundations. To provide a suitable area for constructing the process and auxiliary buildings, a tract of land roughly 4,000 by 6,000 feet was graded to minimum slopes for surface drainage. Altogether, site grading necessitated 9 million cubic yards of excavation and backfill. Several types of fill were permitted, depending on the compaction and bearing capacity required. Fill, classified as Type C, was used primarily to permit all-weather construction of stable fills for building foundations. Type C fill consisted of crusher-run limestone and soil mixed and compacted to achieve 95% of maximum density as determined by ASTM specification D-698 by ordinary rolling equipment without the use of vibratory equipment. Bearing pressure of 4,000 pounds per square foot was allowed for the Type C fill. Approximately 400,000 cubic yards of this type fill were used. A well-compacted base was important for buildings that literally measured in acres instead of square feet. The assurance of a minimum of differential settlement was essential because of the miles of piping that would be mounted in the buildings. At this early stage of the project, a number of activities took place almost simultaneously. Perimeter roads were built around and through the site to allow easy access to locations of construction. Truck alleys needed for plant operation were constructed to facilitate movement of materials and supplies into buildings. Use of precast beams set in place by cranes meant a great saving in time and money. This technique eliminated congestion during construction and reduced the formwork that would have been required to pour the beams in place. In addition to the truck alleys, 22 miles of railroad track and 25 miles of roads were laid inside the plant area. The first buildings erected were of a temporary nature, such as the administration offices, warehouses, cafeteria, and services buildings, together with utilities such as power, water, sewerage, and communications. One of the basic construction materials was concrete. To speed up construction, one central batching and mixing plant was erected to supply all contractors. This plant at the site had a capacity of 200 cubic yards per hour and produced more than 500,000 cubic yards for the project. Daily cement requirement averaged 2,500 barrels. 4 standard mixes of concrete were developed for use, ranging in design strength from 1,000 pounds per square inch to 4,000 pounds per square inch. Transit mixers delivered concrete from the mixing plant to the job. Permanent overhead building cranes capable of handling up to 23 tons were installed early in order to use them for moving heavy equipment as well as pouring concrete. Concrete was poured either directly into forms or transferred to its final location by means of hoppers and power buggies. Mechanical vibrators worked the concrete into place. One of the unusual but important jobs was weather forecasting. Meteorologists at the site issued frequent reports on local weather conditions to contractors so they could schedule work properly and also protect existing construction. In some instances, large areas of fresh concrete were covered with canvas as protection from rain, which was predicted to arrive in a short time as a result of a sudden change in the weather. Approximately 100,000 tons of structural steel were used in the framework of the main buildings. Receiving, unloading, and sorting the thousands of tons of steel at the site on schedule called for efficient teamwork. Standard lumber carriers transferred much of the steel as required for erection by the steel contractors. Fabrication and erection of the structural steel for each of the main process buildings was subcontracted to a separate steel company on a fixed price basis. Specifications required that the steel frame be erected, pinned, and bolted, and then plumbed to a tolerance of -0 and plus 3/8 inch across the joints before final riveting and bolting. As much as 75,000 lineal feet of 5/8 inch cable was used to plumb each building section by section. Permanent connections were made with rivets or high tensile bolts. Iron workers placed and tied approximately 14,500 tons of reinforcing steel for cell floors and equipment foundations, etc. Most of the buildings were of a standard industrial type with concrete foundations and floors, structural steel frames, cement asbestos siding, and steel deck roof with built-up roofing. Functional and plain lined sheets of corrugated cement asbestos siding were bolted to the steel structures. Placement of the base plates for columns of the buildings was held off as long as feasible to permit maximum foundation settlement. After placing at exact elevation, the base plates were grouted beneath by placement of low shrinkage grout. In constructing ground floors of the process buildings, wire mesh was put into place and then concrete poured to form a continuous slab 6 to 8 inches thick. Concrete was struck off by a finishing machine, and finishing by this method speeded up the job and reduced labor costs. Finishing of concrete to precise dimensions was necessarily a hand operation. Roofing was nearly flat, with just enough slope for drainage. The roof was constructed by spot welding a metal decking to structural steel. 1-inch glass insulation was then laid and covered with 4-ply built-up roofing, finished with a wearing course of bituminous cement and pea gravel. Setting the equipment base plates was a job requiring care and precision. First, the anchor bolts were set for a base plate. The bolts were placed in the holes and aligned with wooden templates, and then grout was poured into each hole. The base plates were set to precise elevation and measurement by survey instruments. A level was used to take the elevation off the points that were preset. Each plate was leveled and checked separately, and then both together. After being wedged into position, the foundations were moistened. Grout containing a compound to prevent shrinkage, or long mix grout, was placed under each base plate and packed in tightly to fill all possible voids. To provide power for the Portsmouth plant, the AEC entered into the largest power contract for a single customer in the 75-year-old history of the electric utility industry. A contract calling for 18 billion kilowatt hours yearly, enough for the whole city of New York, or 2/3 of that required for the highly industrialized state of Ohio. Power on this scale could not be provided from existing facilities. So, 15 privately owned utility companies pooled their talents and their resources to create the Ohio Valley Electric Corporation, or OVEC. OVEC undertook to construct 2 large steam electric generating stations. One, 140 miles away at Clifty Creek, Madison, Indiana, with a nominal capacity of 1,290,000 kilowatts. And the other, 50 miles away at Kiger Creek, Gallipolis, Ohio, with a nominal capability of 1,075,000 kilowatts, the largest power plants ever built by private industry. And, more important, among the most efficient plants ever built. each capable of producing 1 kilowatt-hour of electricity on about 7/10 of a pound of coal. In full operation, the power stations use about 7,500,000 tons of coal annually, enough to fill a train of cars stretching from New York City to Miami, Florida. Coal is consumed at the rate of approximately 850 tons an hour, producing a steam flow of 1,341,000 pounds of steam per hour. Transmission of this power from each plant is made over 2 double-circuit lines at a nominal 330,000 volts, equal to the all-time high-voltage record in this country. Each of the circuits has a capacity of 1 million kilowatts for line sections of 50 to 75 miles in length. At the plant, the circuits feed into substations, which consist of switch yards, switch houses, and control houses. Switchyard design is based on the double bus arrangement and the breaker and a half switching scheme. Towers are of the vertical lattice type columns. And in keeping with the record-breaking concentration of electric power, the switchyards required the largest oil circuit breakers ever produced in this country. 330 kilovolt breakers with 2,000 ampere continuous current capacity and the unprecedented interrupting capacity of 25 million kilovolt amperes at 3 cycles. The 330 kilovolts are stepped down by transformers in the outdoor switchyards to 13.8 kilovolts for use in the main buildings. Underground ducts transfer power from the substation to the equipment in the main buildings through an intricate network of electrical conduit, cable, and wiring. Thousands of electric motors, ranging in size up to 2,000 horsepower, require this constant, tremendous power supply, the tab for which is on the order of $70 million annually. Among the largest and most important single operations in the construction work is the fabrication and assembly of the thousands of feet of piping for installation in the huge process buildings. Piping conveys the gas from one stage to another in the gaseous diffusion cascade. More than 600 miles of piping and 1,000 miles of copper tubing were installed in the plant. Great savings in time and money were made by prefabricating more than 100,000 individual piping assemblies and 225,000 pipe hanger assemblies. Welders had to pass rigid qualifications tests to determine the type of work they were qualified to do. This was necessary because of the variety of processes, such as heliarc, electric arc, and acetylene, and the variety of metals and alloys, such as carbon steel, stainless steel, Monel metal, aluminum, and others. At peak effort, 1,200 welders were employed. Altogether, the plant required 620,000 lineal feet of automatic and hand welding on pipes ranging from 1/4 inch to 4 1/2 feet in diameter. Because of the highly corrosive nature of uranium gases, all steel piping had to be lined with pure nickel. In addition, cleanliness control was essential, since the process gas is so highly active that it combines and reacts with almost every substance, forming solids which can clog the entire system. Therefore, cleanliness is extremely important. Sections of pipe were dipped in chemical reagents in huge cleaning vats to remove foreign matter. Each piece of piping is almost literally handled with kid gloves to prevent contamination with dirt, dust, or water. After dipping and cleaning, the ends of the pipe were sealed to prevent dirt from entering until the piping was welded in its proper place. The bakery, with the clean floor you could eat off, was nothing compared to Portsmouth. Floors were not only swept, but vacuum cleaned to be spotless. Even the air pressure inside the buildings was kept higher than on the outside to keep dust from getting in. Portsmouth resembled a 3-ring circus as construction went on simultaneously on all fronts. During this period, it was necessary to train operators and workers to operate the units as they went on stream. Goodyear Atomic Corporation, the operating contractor, sent key engineers and technicians to Oak Ridge and Paducah, where they were taught the know-how of running a gaseous diffusion plant. These men formed the basis of the training staff at Portsmouth. every modern teaching aid was used to expedite training. Lectures, workshops, models, motion pictures, mock-ups, and actual equipment. Thus, as the units in the main plant were completed, the operating crews took over. One of the important factors in the choice of the Portsmouth site was availability of water, primarily the Scioto River, 4.5 miles away. Ample water is assured due to the average annual precipitation of approximately 38 inches over the 6,500 square miles of the watershed. Wells were drilled in the floodplain to provide a water supply during construction. After completion of the plant, the wells serve as a permanent source of supply for the sanitary and fire water systems. At the river, a pumping station was erected with a capacity of 40 million gallons daily. The raw water is piped through a pipeline 4 feet in diameter to the water treatment plant at the site and is mixed with coagulants and suitably treated to reduce the formation of harmful deposits in the process recirculating water system. Since great quantities of heat are produced during the gaseous diffusion process, principally heat of compression, the construction plans called for each of the process buildings to have water cooling towers to remove the heat. The towers were erected on concrete slabs 20 inches thick. Huge forms were used and reused in the pouring of concrete for the walls. Columns and beams, prefabricated in another area, were hauled to the site on trucks and set into place by cranes. Precast beams with interlocking joints were assembled and rods placed in the pipes in the beams. After they were in place, grout was poured into the pipes to hold the rods in place. Redwood was used in the superstructure of the towers to reduce decay. The flow of water through the towers is at the rate of 689 million gallons daily. Of this amount, approximately 20 million gallons daily evaporate into the air, expelling 7 billion BTUs, enough to heat 70,000 average homes. Perhaps one of the most unusual features of the Portsmouth plant is that the production operation is largely automatic. It is undoubtedly an outstanding example of automation. Control is achieved through delicate instruments, which are connected to operating equipment by means of tubing. More than 1,000 miles of tubing thread through the plant, eventually ending in the control room. Thus, there is immediate and automatic detection of any malfunction, such as a burned-out motor, an increase in pressure, a broken compressor blade, a clogged barrier, etc. Essential to the operation of the main plant are the various auxiliary services. Some, like the fire department, have to be alert, ready for action at any time. Security and plant protection also are never-ending day and night jobs. Others, like the process laboratories, have special facilities for trained personnel to make constant tests and studies that are vital to keep the plant in operation. And, always important, are the hospital services, water sanitation, sewage disposal, repair shops, heating systems, the cafeteria, and the administration offices. All of these make the plant a complete entity, able to take care of itself. About 2,600 workers are needed on the permanent staff. And so, as the water vapor rises in the sky, indicating the Portsmouth plant is on stream, let's summarize some of the accomplishments on the project. 2 are of particular significance. First, completion of the plant several months ahead of schedule. And second, achieving a saving of about 34% below cost estimates, a cash saving of approximately $400 million. The reasons for the economy were the mutual exchange of efficient methods among the contractors and the benefit of past experience at Oak Ridge and Paducah. Savings achieved through lower costs of materials and equipment were $170 million. One of the contributing factors in money saving was the maximum use of the same equipment, such as formwork, for operations of a repetitive nature. Savings in labor costs were a result of the shorter construction period, the even distribution of forces, repetitive nature of work, and the excellent cooperation between labor and management to prevent work stoppages. This saving amounted to $196 million. And more important than the saving is the significant contribution made by the plant in the production of uranium-235 for military use in defense of our way of life and for the peaceful application in the arts of humanity and progress.